there's something peculiar about the way we talk about reality. We see a thing either is or it isn't. A door is open or closed. A coin shows heads or tails. A cat is alive or dead. This is the logic we breathe like air, so natural. We forget it's just a framework, a set of assumptions we've built our entire civilization upon. And it works beautifully, magnificently even, for everything we can touch and see. But descend to the scale of atoms, to the realm where matter reveals its true character. And this logic, this either-or certainty, that spews so solid simply dissolves. Not because we lack better instruments or cleverer mathematics, but because nature at that scale doesn't operate by the rules we've assumed are universal. The opposite of a correct statement is a false statement, yes. But the opposite of a profound truth may well be another profound truth. And if you think that sounds like I'm speaking in riddles, well, perhaps that tells us something important about the riddle itself. Let me start with something concrete, something you can picture. Imagine you're standing in a dark room with a single candle. You want to know where the candle is, so you look at it. Simple enough. The light travels from the candle to your eye, and you see it. The act of observation. The seeing doesn't change the candle's position. It was there before you looked, it's there while you look, it will be there after. This is what we might call the classical picture of reality. Objects have properties: position, velocity, color, temperature, and those properties exist independently of whether anyone is paying attention. The universe in this view is like a vast machine ticking along according to fixed laws, and we are simply observers fortunate enough to peek inside and watch the gears turn. Now consider an electron. You want to know where it is, but you cannot simply look at it the way you look at a candle. To observe an electron, you must interact with it, shine light on it perhaps, or pass it through a magnetic field. And here's where everything changes. The very act of measuring its position disturbs it. The light you use to see it carries momentum, and when that light bounces off the electron, it gives the electron a kick. You can measure the position with exquisite precision, yes? But in doing so, you've changed the electron's velocity in an uncontrollable way. But you can measure its velocity precisely, but then its position becomes fundamentally uncertain, not because your equipment isn't good enough, not because you're clumsy, but because, and here we must speak carefully, the electron doesn't have both a definite position and a definite velocity simultaneously. Not in the sense that we use those words for candles and coins. This is what Werner Heisenberg discovered, and it shook the foundations of physics, the uncertainty principle, as it came to be called. But even that name is misleading, because it suggests we are simply uncertain about something that's really there, as if the electron has a precise position and momentum, and we are just too crude to measure both at once. That's not what's happening. What's happening is far stranger and far more profound. The electron does not possess both properties at the same time. Ask nature where the electron is, and you get an answer. Ask nature how fast it's moving, and you get an answer. But ask both questions together, and nature, not your equipment, not your theory, but nature itself, cannot provide both answers. This isn't ignorance. This is the way things are. You see the problem now. Our language was built for a world of candles and coins, of objects that have properties whether we look or not. But electrons, photons, atoms, they don't fit into that language. They can't. And so we're forced to describe them using concepts that seem to contradict each other, concepts that in the classical world would be mutually exclusive. We must talk about waves and particles. We must talk about being in multiple places at once until we look, then being in only one place once we do look. We must accept that the act of observation is not passive. It participates in creating the reality we observe. And if that makes you uncomfortable, if it feels like reality is slipping through your fingers, then congratulations. You're beginning to understand. Let me show you what I mean with an experiment. It's become famous, almost too famous, but that's because it cuts straight to the heart of the mystery. Take a source that emits electrons one at a time. Aim them at a barrier with two slits in it. Behind the barrier, place a screen that lights up wherever an electron hits. Now, common sense classical intuition tells you what should happen. Each electron is a particle, a tiny bullet of matter. It goes through either the left slit or the right slit. and it hits the screen somewhere behind that slit. Fire enough electrons and you should see two bright patches on the screen, one behind each slit. Simple, but that's not what happens. Instead, you see a pattern of bright and dark bands spread across the screen, an interference pattern, the kind of pattern you get when waves overlap, when the crests of one wave meet the crests of another and amplify, or when a crest meets a trough and they cancel out. This is the pattern water makes, the pattern sound makes. It's a wave pattern where we're firing particles one electron at a time. How can a single particle interfere with itself? How can it go through both slits at once? You might think, well, perhaps the electrons are influencing each other somehow. So, you slow down the source until it's only one electron in the apparatus at a time, one electron emitted, traveling through space, hitting the screen, and only then is the next electron released. The interference pattern still appears. Each electron, traveling alone through the apparatus with no other electrons anywhere nearby, somehow produces a pattern that requires going through both slits simultaneously. It's as if each electron is a wave that spreads out, passes through both openings, and interferes with itself. But here's where it gets truly strange, where the classical picture doesn't just bend, but breaks entirely. Suppose you decide to find out which slit the electron actually goes through. You place a detector near each slit, a device that clicks if an electron passes nearby. Now you fire the electrons again, and every single time one detector clicks and the other doesn't. The electron goes to one slit or the other, never both, just as classical intuition insisted it should. But look at the screen now. The interference pattern has vanished. In each place, two bright patches, exactly what you'd expect from particles going through one slit or the other. The mere act of checking which path the electron takes destroys the wave-like behavior. The electron behaves like a wave when you're not looking at which slit it goes through, and like a particle when you're looking. Both descriptions are necessary to account for what we observe. Both are correct in their context, but they contradict each other, and yet both are required. This is what I mean by complementarity. Note that electrons are sometimes waves and sometimes particles, as if they switch costumes depending on the experiment. It's that wave and particle are complementary descriptions, each capturing part of the truth, neither capturing all of it. You need both to have a complete account, but you can never use both simultaneously. The experimental setup that reveals the wave nature makes the particle nature inaccessible, and vice versa. It's not a limitation of our technology, it's a feature of reality itself. The properties we assign to quantum objects depend on how we choose to observe them. The question, what is the electron really doing when we're not looking, doesn't have an answer, because what it's doing is a concept that only makes sense in the context of an observation. Without the observation, without the interaction that constitutes the measurement, the question is meaningless. Not unknown, meaningless. I can see the objection forming in your mind. Surely you want to say, surely the electron has to be somewhere, doing something, whether we look or not. Surely reality exists independently of, and I sympathize with that intuition truly. It's the intuition I grew up with, the intuition every physicist before the quantum revolution grew up with. But quantum mechanics forces us to abandon it, or at least to recognize its limits. Between measurements, between observations, the electron exists in what we call a superposition or combination of all possible states at once. It's not that we don't know which state it's not in any particular state, it's in all of them simultaneously, each weighted by a certain probability amplitude. Let me put it differently. Think of the electron's wave function, the mathematical object that describes its quantum state. Before you measure the electron's position, the wave function spreads throughout space. It has non-zero amplitude at many different locations. In regions where the amplitude is large, the electron is more likely to be found if you measure its position there. In regions where the amplitude is small, it's less likely. But until you measure, the electron isn't at any of those places. It's in the superposition of being at all of them. The measurement, the interaction that constitutes observation, causes the wave function to collapse. Suddenly, the electron is found at one definite location, and the wave function that was spread out becomes concentrated at that point. We get a single outcome from many possibilities. This collapse is irreversible and unpredictable. Given the wave function before the measurement, we can calculate the probability that the electron will be found at any particular location, but we cannot predict which specific outcome will occur. The universe at this fundamental level is not deterministic. It doesn't follow a predetermined script. Einstein hated this. He famously said God does not play dice with the universe, to which I could only reply that we shouldn't tell God what to do. The evidence is overwhelming. Quantum mechanics is probabilistic at its core, and no amount of wishing will make it otherwise. But let's be clear about what this means and what it doesn't mean. It doesn't mean anything goes, that the universe is chaotic or arbitrary. Quantum mechanics is exquisitely precise. The probabilities it predicts can be calculated to extraordinary accuracy and have been confirmed by experiment billions of times. When we say the outcome is unpredictable, we mean it's unpredictable even in principle, even with perfect knowledge of the system. Not because we're missing information, but because the information doesn't exist until the measurement creates it. The act of observation doesn't reveal a pre-existing property. It brings that property into being now. You might still be holding on to the hope that there's some deeper layer, some hidden variables beneath the quantum description that determine outcomes in a way we just haven't discovered yet. Perhaps electron really does have a definite position and momentum, and the wave function is merely a statistical description of our ignorance, like the way we describe a coin flip without knowing all the forces acting on the coin. This was a respectable position. Many brilliant physicists thought so. But John Bell, decades after these debates, proved mathematically that no local hidden variable theory can reproduce all the predictions of quantum mechanics. And experiments testing Bell's inequalities have confirmed quantum mechanics and ruled out local realism. The universe really is as strange as quantum mechanics says it is. Let me ground this in something tangible, something you've used today. Your smartphone, the computer you're watching this on, the GPS satellites orbiting overhead, all of them depend on quantum mechanics being correct. Not approximately correct, not good enough for government work, but fundamentally, precisely correct. Transistors, the building blocks of every electronic device, work because electrons can tunnel through barriers they classically shouldn't be able to cross. Quantum tunneling. An electron encounters a potential barrier higher than its energy. Classically, it should bounce back, but quantum mechanically, the wave function extends into and through the barrier, giving the electron a non-zero probability of appearing on the other side. It's as if you roll the ball toward a hill. The ball didn't have enough energy to roll over the top, and yet you found it on the other side anyway. Impossible classically. Routine quantum mechanically. And that process happens trillions of times per second in your computer's processor. Lasers work because of stimulated emission, a quantum process where photons in identical quantum states trigger atoms to emit more photons in that same state, creating coherent light. MRI machines depend on nuclear magnetic resonance, the quantum mechanical interaction between atomic nuclei and magnetic fields. Atomic clocks, the most precise timekeepers ever built, measure the frequency of light absorbed or emitted by atoms in specific quantum transitions. These technologies don't work because quantum mechanics is a convenient approximation. They work because quantum mechanics describes reality with breathtaking accuracy. The theory has been tested in every conceivable way and it has never failed, not once. But let's return to the philosophical implications, because that's where the real profundity lies. Classical physics painted a picture of the universe as something external to us, something we could study objectively without affecting it. The observer and the observed were separate. We could, in principle, know everything about a system, its complete state at one moment, and from that predict its entire future and reconstruct its entire past. The universe was deterministic, mechanical, comprehensible in the sense that it operated by laws we could discover and understand fully. Our role was simply to observe and describe. We were not participants. We were audience members watching a play whose script was written at the moment of creation. Quantum mechanics demolishes that picture. The observer is not separate from the observed. Observation is a physical interaction, and that interaction is part of the system. We cannot stand outside nature and look in, because we are part of nature. Our measurements don't just reveal reality, they participate in its creation. And this isn't mysticism or wordplay. This is what the mathematics demands, what the experiments confirm. The wave function describes potential, possibility, the measurement actualization, specificity, and you cannot have the actualization without the measurement. The properties we assign to quantum objects, position, momentum, spin, don't exist in the definite form we're used to until we measure them. Before measurement, there are only correlations, potentials, probabilities. You might ask, what counts as a measurement? What counts as an observer? Must it be a conscious being, a human with intentions and awareness? No, that way lies confusion. A measurement, in the quantum sense, is any interaction that entangles the quantum system with a macroscopic apparatus in an irreversible way. When an electron hits a screen and leaves a mark, that's a measurement. When a photon is absorbed by a detector and triggers an electrical current, that's a measurement. The universe is full of measurements, countless interactions that collapse wave functions and turn potential into actual. Consciousness is not required. What's required is an irreversible amplification that takes the quantum event and magnifies it to the classical level where it leaves a permanent record. But here's the deep question, the one that keeps physicists awake at night. If measurement collapses the wave function, if observation turns superposition into definite states, then what about things we don't observe? What about the vast reaches of the universe where no measurements are being made, no interactions with macroscopic apparatus, no records being created? Is a wave function of the entire universe in a superposition of all possible states? And if so, what causes that to collapse? Some have suggested that consciousness plays a role, that the universe needs observers to become real. I find that unnecessarily anthropocentric. Others have proposed that the universe constantly splits into parallel branches, one for each possible outcome, and we simply find ourselves in one branch. That's the many worlds interpretation, and it avoids collapse entirely, though at the cost of an infinite proliferation of universes. My own view, the view that has come to be called the Copenhagen interpretation, is more modest. It says, quantum mechanics is a theory about observations and measurements, not about an underlying reality independent of observation. The wave function is not a description of what things really are when no one is looking. It's a tool for calculating the probabilities of measurement outcomes. And the question, what is really happening between measurements, is not a scientific question, because science deals with what can be observed and tested. If something in principle cannot be observed, then speculating about it is metaphysics, not physics. This doesn't mean there is no reality independent of observation. It means that quantum mechanics doesn't tell us about that reality. It tells us about the interface between the quantum world and the classical world, the boundary where the potential becomes actual. Some find this unsatisfying. They want physics to tell them what's really there, not just what they'll see when they look. But I think this is asking too much, or perhaps asking the wrong question. Physics has always been about describing observations, predicting outcomes, finding patterns in what we measure. Classical physics created the illusion that it was describing an objective reality, but that was only because the effects of observation were negligible. At the quantum scale, those effects are unavoidable and fundamental. The classical limit, where things behave like objects with definite properties independent of observation, emerges as a special case when quantum effects average out over large numbers of particles, or when decoherence destroys the delicate superpositions. But the quantum picture is more fundamental, and there's a beauty in this if you can see it. Quantum mechanics doesn't rob the universe of meaning or reduce it to meaningless probabilities. Rather, it reveals that reality is richer, stranger, more subtle than we imagined. It shows us that complementary descriptions, wave and particle, position and momentum, determinism and probability, are all needed to capture the full picture. That nature refuses to fit into the boxes we've prepared for it. That the boundary between observer and observed is not a clean line, but a participation, an entanglement. We are not outside nature looking in. We are part of nature, and our observations are part of the process by which possibility becomes actuality. Let me offer an analogy, imperfect as all analogies must be when dealing with quantum phenomena. Think of a shadow. Is a shadow a thing or the absence of a thing? It's both and neither. It's a pattern created by the interaction of light and an opaque object, and it cannot be understood by studying either alone. You need the light, you need the object, and you need a surface on which the shadow falls. The shadow doesn't exist independently. It's a relational phenomenon arising from the configuration of the whole system. Quantum properties are like that. They don't exist in the electron or photon. They arise from the relationship between the quantum system and the measuring apparatus. Ask about the electron's position, and the relationship yields a position. Ask about its momentum, and the relationship yields a momentum. But you cannot ask both at once, because those relationships, those experimental arrangements, are mutually exclusive. Now, I want to emphasize something that's often missed in popular accounts of quantum mechanics. This isn't just about tiny things. It's not that quantum weirdness only matters for electrons and photons, while our everyday world remains safely classical. The classical world emerges from the quantum world. Everything is made of quantum particles obeying quantum laws. The reason your coffee cup doesn't spontaneously turn through the table, the reason you don't diffract when walking through a doorway, is that for macroscopic objects made of countless particles, the quantum effects that would produce such behavior are impossibismal. The probabilities become so tiny, the required coherence so fragile, that for all practical purposes, the classical approximation is perfect. But in principle, it's all quantum. The classical world is the quantum world in the limit where quantum interference effects cancel out or become undetectable, and we're getting better at pushing that boundary. Physicists have now demonstrated quantum superposition and interference not just with single particles, but with molecules containing dozens or even hundreds of atoms. They've entangled photons separated by hundreds of kilometers. They created quantum computers that exploit superposition and entanglement to solve certain problems exponentially faster than classical computers ever could. They built experiments that close all the loopholes in tests of Bell's inequalities, confirming beyond any reasonable doubt that quantum mechanics, with all its strangeness, is how nature actually operates. The evidence isn't subtle, it's overwhelming. But quantum mechanics also teaches humility. It shows us that there are limits to what can be known, and those limits are not imposed by our technology or ingenuity, but by nature itself. You cannot measure position and momentum simultaneously with arbitrary precision. You cannot determine both the wave and particle properties in a single experiment. You cannot know the quantum state of a system without disturbing it in a way that makes your knowledge immediately obsolete. And most fundamentally, you cannot predict the outcome of a single quantum measurement. You can only calculate probabilities. This is not a temporary limitation awaiting a more complete theory. This is the structure of reality at the deepest level we've been able to probe. Some see this as a defeat, as if physics has stumbled against a wall and admitted failure. I see it differently. Physics has revealed the architecture of possibility itself. It has shown that the universe is not a mechanism wound up at the beginning of time and ticking along a predetermined path. It has shown that the future is not written, that novelty genuinely emerges, that creativity and unpredictability are woven into the fabric of nature. At every quantum event, the universe makes a choice, not a conscious choice, but a genuine selection from among real possibilities. And those choices accumulate layer upon layer, building the complexity we see around us, from atoms to molecules to cells to minds to civilizations, all of it resting on the quantum foundation where the possible becomes actual moment by moment. There's something deeply democratic about quantum mechanics, if I may use that word. In the classical picture, if you knew everything about the present, you could calculate everything about the future. Knowledge was, in principle, complete and total. But quantum mechanics says no. Even with perfect knowledge of the wave function, even with complete understanding of the laws and initial conditions, you cannot predict individual outcomes. Probability is irreducible. The universe retains an element of surprise, a capacity for genuine novelty that no amount of information can eliminate. We are not cogs in a machine. We are participants in an unfolding story whose ending is not yet written. And yet, For all we seem determinacy at the quantum level, the world we experience is remarkably stable and predictable. The sun rises each morning not despite quantum mechanics, but because of it. The atoms in your body, the molecules in the air, the rocks and oceans and stars, they're stable because quantum mechanics allows only certain states, certain energies, certain configurations. Atoms have discrete energy levels, not because of some arbitrary rule, but because they are quantum systems, and quantum systems have quantized properties. The periodic table, the chemistry that makes life possible, the stability of matter itself, all of that emerges from quantum mechanics. The same theory that says individual events are unpredictable also says that collections of many events follow precise statistical laws. Paradox upon paradox, complementarity upon complementarity. Let me bring this back to where we started. We began with the observation that reality seems to follow simple either-or logic. A thing is or isn't. But at the quantum scale, that logic fails. An electron is in multiple places until you measure it. Then it's in one place. A photon goes with both slits until we check, then it went to one slit. The wave function contained all possibilities until observation selects one actuality. This isn't their failure of understanding, it's a feature of nature. A classical world with its definite properties and deterministic evolution is an approximation that emerges when quantum systems become large and interact with environments in ways that destroy coherence. But beneath that approximation, beneath the surface of everyday experience, reality is quantum. And quantum reality doesn't play by the rules we thought were universal. So what does this mean for us? What does it mean to live in a quantum universe? It means we must revise our notion of what it means to know something, to understand something. It means accepting that there are questions without answers, not because we ignore them, but because the questions presume a picture of reality that nature doesn't support. It means recognizing that the observer and the observed are entangled in a way that cannot be undone. It means appreciating that the universe is more subtle, more strange, more marvelous than the mechanistic picture allowed. And perhaps most importantly, it means being comfortable with complementarity, with the idea that contradictory descriptions can both be necessary and both be true. Quantum mechanics has given us extraordinary power. We can manipulate individual atoms, design materials with properties that don't exist in nature, perform computations that would take classical computers longer than the age of the universe. We've harnessed the quantum world to build technologies our ancestors would regard as magic. But quantum mechanics has also revealed limits, not to what we can do, but to what we can know. And perhaps that's the deepest lesson of all. Nature does not give up all her secrets. She reveals herself only in response to our questions, and the answers depend on what we ask. The universe is not a book written in the language of mathematics waiting to be read. It's a conversation, and we are participants in it, shaping the questions and receiving the answers that our questions make possible. I spent my entire life thinking about these problems, arguing with Einstein and Heisenberg and Schrödinger and all the others about what quantum mechanics means. And I've come to believe that the right response to quantum mechanics is not frustration, but awe. Not disappointment that we can't know everything, but wonder that we can know so much. We've glimpsed the machinery beneath the surface of things, and it's far stranger than anyone imagined. We've learned that reality at its foundation is not made of stuff, but of relationships, not of things, but of processes, not of fixed properties, but of potentials awaiting realization. And that realization, that transformation from possible to actual happens moment by moment, interaction by interaction, observation by observation throughout the universe. We are not outside observers of a mechanical universe. We are participants in a quantum universe where observation matters, where measurement shapes reality, where the boundary between mind and matter, between subject and object, is far more porous than classical physics ever suggested. And that depth seems unsettling if it seems to undermine the solid ground of objective reality we thought we stood on, and perhaps it's time to find a new place to stand, not on false certainty, but on something more honest, the recognition that we are part of this universe, not separate from it, that our observations are physical acts with physical consequences, that knowledge is not passive reception but active participation. And that the universe, in all its quantum strangeness, is far more interesting than the clockwork mechanism we once imagined. Physics has given us power to manipulate atoms, to harness quantum phenomena, to build technologies that reshape civilization. But it has also shown us the boundary of what can be understood, the edge where our classical concepts fail, and we must speak in complementary descriptions that contradict each other, yet both capture truth. And perhaps that is the deepest lesson of all, not that we know everything, but that we know the shape of what we cannot know. Not that we've solved all mysteries, but that we've discovered which mysteries are fundamental to the structure of reality itself. That's not defeat, that's progress. That's wisdom. That's what physics, at its best, has always been about. Learning to ask the right questions, accepting the answers nature gives us, even when they overturn our intuitions, and building on that foundation a deeper, truer, more honest understanding of the world we inhabit, and of ourselves as conscious beings made of quantum particles, trying to understand quantum particles.